Welcome back. We've finally made it to chapter 12, that giant behemoth of a chapter, which covers so much material that I broke it up into two homework assignments. One of the very first topics introduced in the chapter is the subject of rotational kinetic energy. And I think a lot of you will find this conceptually appealing. There's a lot of new formula presented in this chapter, and that's one of the reasons for breaking it up into two pieces. Okay, so here's my lame drawing of a propeller. Let's say this is on the front of an old airplane, and the blades of the propeller are spinning at some particular rotational speed. That's the Greek letter omega. The SI units of omega would be radians per second. And remember, a radian is dimensionless, so that's really just per second or inverse seconds. You could also describe the rotational speed in revolutions per minute, or even degrees per minute, degrees per second, as long as it's an angle over a time. And what we're interested in finding is the total kinetic energy associated with this rotating propeller. Because we know that the kinetic energy of a particle, K particle, is 1/2 mv squared, v squared, where m is the mass of the particle and v is the speed of the particle. Well, a propeller is made up of a whole bunch of particles, if you want to think of those particles as being atoms. How many atoms? Well, that's not really a topic for 3A, but we're talking about 10 to the 24th or 10 to the 25th atoms. Of course, that's not something that was known until the early 1900s, just how many atoms we're talking about. So obviously it would be implausible to calculate the kinetic energy of each individual atom within this propeller and then add all of those up. How can you possibly add up a number of quantities that large? There's no time in the universe to do that. But you'll see it's very easy actually to express the total kinetic energy. So let's start by grabbing an arbitrary little particle here. So I put a little box. Now, atoms, of course, are way smaller than that. But let's just suppose that we had chopped this whole thing up into something like 1,000 pieces. And then we labeled them all. Mass 1, mass 2, mass 3, etc., all the way up to like mass 1,000. So maybe this is mass 657. It really doesn't matter. But I'm going to call this M sub I. I is the index. I could be, if we really did chop this into 1,000 pieces, I could be a number anywhere between 1 and 1,000. And for this particular piece, I think I said, what, 657? And let's consider the motion of this little piece of mass within the propeller blade as the blade spins. Now we know that the propeller is mounted on a fixed axle. So as it spins, hopefully you can see that the path traced out in space, that's not a good circle at all, is circular. If you could watch this little piece of mass, it's moving around in a circular path. The propeller does not actually have to be circular in shape for that to be true. In fact, it could be any shape as long as it's being forced to rotate about a fixed axle or axis. Every piece of the propeller will be moving in a circle. And that's assuming it's a rigid object, right? If this was a big blob of jelly, then maybe as you spun the jelly, maybe this piece would get stretched out or in, and it wouldn't be a circle. But for a rigid object rotating about a fixed axis, each piece of the object traces out a circle. And that's great because we have some formulas for circular motion. So I'll remind you once again, if you're looking at something moving in a circle of radius r, if it traces out a distance ds, I'll call this little piece of arc length ds, then simultaneously it would have, or in doing so, it would have traced out, or swept out, I should say, an angle which I will call d theta. That's this tiny little angle here. So it moves through a distance in meters ds while sweeping at an angle d theta. And let's say it does that in a time dt. Well, you should know these formulas by now, but the velocity, and your book calls it tangential velocity, but that velocity would be the ratio arc length to time, right? It's just distance over time, meters per second, miles per hour, whatever. But we can express that in terms of r and d theta, because you should also remember the relation between d theta, ds, and r. Remember the definition, where's a good place to put this? The definition of that angle is arc length compared to radius. If the arc length was equal to the radius, like if you had traced out a full radius around the circle, this would be radius over radius, or 1. That angle would be, by definition, 1 radian. Of course, in this picture, it's much less than. Let's say this is 1/10 of a radius. Then this angle, by definition, would be 1/10 of a radian. Okay, so solve this for ds, and it's r d theta. So I'm going to put that over here, r d theta over dt. And then you should recognize this. Look at the units. Radians per second, or revolutions per minute. This is angular velocity, omega. So I'm just reminding you where this comes from. V tangential is r omega. If you happen to know the rotational speed in radians per second, then you can just multiply by r, and you'll get the tangential speed in meters per second. That's if you plug in radius in meters. Now, just a moment ago, I said this could be in revolutions per minute. I should qualify that this equation's not valid unless this is in radians per second, because this equation, remember, this comes from this, and this equation is the definition of an angle in radians. So this is only applicable if you've measured your rotational speed in radians per second. Okay, so since we're looking at the ith particle in this propeller, I'm going to describe its kinetic energy. The kinetic energy of the ith particle would be 1/2 times the mass of the ith particle times the tangential speed of the ith particle squared. And it's a little unnecessary to specify tangential speed, because that's the only speed. If you're wondering why even have that subscript, it's because the most general type of motion could involve something circling but also spiraling outwards. So it may have, in addition to its tangential velocity, it could also have some outward or inward velocity. And that's why your book specifies tangential velocity. But in this case, the motion is purely circular, and it's the only velocity that we have to worry about. Okay, so here I will substitute. The tangential velocity of the ith particle would be the distance of the ith particle from the axis. So I'm going to label that distance. Here's r sub I. That's supposed to say sub I. And notice that that distance depends on which particle you're looking at. If we looked at a particle at the tip of the propeller blade, that particle would be farther from the axis of rotation, and so r would have a greater value. So r does depend on which particle you're talking about. Here's where I will plug in r sub I omega squared. So instead of V tangential, I'm using this expression. Now, hopefully, you're a detailed observer here, and you've wondered, why am I not putting the subscript next to omega? R certainly depends on the particle, right? This particle has a shorter radius of circular motion than does a particle at the tip. But the whole idea is that this is a rigid rotating object, rigid extended object. Every piece of this propeller is moving together with the same rotational speed. If it wasn't, or if they weren't, then the whole thing would be breaking apart. So by assumption, omega is the same for everything, and that means we do not need a subscript on omega. Okay, the next step is super easy. This is the kinetic energy of just a single particle. We are looking for an expression for the kinetic energy of the whole thing. Every little piece of this propeller is moving. That means every little piece has kinetic energy. If we add up all those kinetic energies, remember they're scalars, so we can do that, we should get an expression for the total kinetic energy. So right here, I'll say K total, or just K rots for rotational. The rotational energy of the entire thing would be the sum over I of K, the sum over I of K sub I. So what this means is take K1, the kinetic energy of mass 1, and add to that K2, the kinetic energy of mass 2. Just in case it's not clear to you, if you're not too familiar with this notation, that's what this means. Just add up the kinetic energies of all the little pieces. Well, that means adding up all these expressions. So that's the sum over I of 1/2 m sub I r sub I. And what I'm going to do now is square both quantities inside the parentheses. R sub I squared, omega squared. And before I do something cute with factoring. I'll just write it out to make this easier. Remember, this means the sum of all these terms for every value of the index I. So that's 1/2 m1 r sub 1 squared omega squared plus 1/2 m2 r sub 2 squared omega squared plus. You get the idea? And I'm hoping you recognize that every one of these terms from here out to 10 to the 23rd, if that's how many particles we're talking about, every one of these terms has something in common. They all have a 1/2 out front, and they all have an omega squared at the end. So I'm going to factor those out to the left and the right, and I've got 1/2 times m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus dot, 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 and then the omega squared on the right side. After you distribute the 1/2 and the omega squared to everything inside, you would be back to this expression. Now, this is obviously a cumbersome way of expressing the result, so why don't we try to write it more compactly? The total kinetic energy associated with the rotation of this rigid object would be 1/2, and I'm going to use the summation notation again. So I'll put this whole thing in parentheses. Let's take the sum of m sub I r sub I squared, sum over all values of I. Again, this is a prescription that says, okay, take each mass, multiply by the square of its distance from the axis of rotation, and then add all those up. That's it. So here it is. That really wasn't too much work. That's our formula for the rotational kinetic energy of an extended object. How do you go about calculating it? Well, you've got to take every little piece of your object, take its mass, multiply by the square of its distance from the axis, and then add all those up. Now, if you're talking about 1,000 pieces, 10,000, or a trillion in the case of actual atoms, that's going to take forever. And why would you want to do that for every single problem? Well, it turns out that for a variety of regular common shapes, this entire thing boils down to one simple formula. So first we need a name for this. Most books call this the moment of inertia. Moment of inertia. I like to call it it doesn't really matter, both labels are fine, but I like to call it the rotational inertia. Rotational inertia, and almost universally everybody uses the letter capital I for this quantity. And with that label, we can rewrite this even more compactly as K rotes ma goats is 1/2 times the moment of inertia times omega squared. There it is. The first formula from this chapter that you should memorize. You don't want to be going to the note card for this. If you're going to the note card, that means you probably didn't learn this stuff well enough. And it shouldn't be difficult to memorize because compare it to the kinetic energy for a particle. 1/2 mv squared. Do you see how similar they are? We still have the 1/2, but instead of regular old mass and what is mass, one way to think about mass is as a measure of an object's inertia. How difficult is it to accelerate? Remember F equals ma? The more inertia something has, the lower its acceleration for a given force. It's really hard to, I don't know, let's say you had a bunch of kids on roller skates and one of these kids is like 200 pounds. Isn't it going to be a lot harder to shove that kid and get them moving than the 50-pound kid? Right? The more mass you have, the more inertia you have, the greater the tendency to resist changes in velocity, which is really just an imprecise way of saying the lower the acceleration. The more force it takes to produce a given acceleration. Okay, so mass here, this is hence the name, rotational inertia. We're going to see that this quantity is a measure of not how difficult it is to get something moving in a straight line, the way M tells us, or as M tells us about a particle, but how difficult it is to get something to rotate. So one of the examples we'll look at is a rod. This is not really a rod, but think of this as a thin rod. We're going to see that when you rotate a rod about an axis through the middle, these are award-winning graphics here, an axis through the middle, the moment of inertia is less than if you were to try to rotate this ruler about an axis through one end. This has more rotational inertia in this configuration than it does in this configuration. So moment of inertia captures not just the total mass, but also how the mass is distributed, which is worth repeating. moment of inertia is a number that quantifies not just the mass, but the way in which the mass is distributed. You can see that if you have more mass far from the axis, if the values of these various radii were greater, then r squared would be greater, and that means the entire quantity would be greater. So moment of inertia goes up if your mass is distributed farther from the rotational axis. That's really something you want to understand about the definition of moment of inertia. Okay, now usually you're not actually going to calculate moments of inertia by adding up these quantities for a bunch of particles. So let's look at, case in point, the propeller. We don't want to deal with 10 to the 25th or 26th particles. That's insane. So what we do, impossible. Instead, let me just draw some arbitrary blob here. I don't know, maybe this is a piece of dough that you're trying to turn into a pizza. So you're spinning it about this axis. The axis goes right through this point right here. And this whole thing is spinning around like this. Rather than chop this up into 1,000 pieces or whatever, let's chop it into an infinite number of pieces. You see, if each little piece has infinitesimal size, which means I'll call it dm, then there are an infinite number of them. It's that whole calculus idea. An infinite number of infinitesimal little things can still add up to some finite thing. So if this whole thing is, now dough's not really rigid, is it? But let's pretend this object is rigid, in which case there's a single value for the rotational speed. Again, every one of these particles is going to be tracing out a circle. So here's the circular path traced out by this individual little thing. And because it's moving in a circle, it has a speed, and that means it's got a kinetic energy. So dk, I'm going to use the symbol dk for the infinitesimal quantity of kinetic energy associated with this infinitesimal piece of mass. Well, that would be 1/2 times dm, the mass, times v squared, where it's understood that this speed is the speed of that infinitesimal little piece. Now, by the same reasoning as before, that little piece of mass has a particular distance from the axis, which I'll call r, and we could rewrite the speed as follows. That's r omega squared. So this time, I no longer have the subscript I to distinguish the masses, but it's understood, that's a defect of the notation here, but it's understood that dm is just some arbitrary piece of mass here, and r is the radius between the axis and that particular piece of mass. R is going to depend on which piece of mass you're looking at. A little chunk of mass over here would have a greater value of r. All right, and what are we trying to do here? Well, this would be the kinetic energy of an infinitesimal piece. We want the total kinetic energy. And instead of using the Riemann sum notation, the Greek letter sigma, let's use the fancy calculus symbol that I think was introduced by Leibniz. Let us sum up. Remember, this is a big script S. The integral sign is a script S. Sum up all the infinitesimal kinetic energies to get the total kinetic energy associated with the rotation of this rigid object. Okay, so that's the integral of 1/2 dm r omega squared. And just like before, omega is not a quantity that changes from one little piece of mass to the next. It's a constant for this rigid rotating object. So is the 1/2. So let's take the 1/2 and pull it out front. You know, you can pull out constants. I'm also going to pull out the omega squared, but I would prefer to write it on the right side, and you'll see why. So that's 1/2 integral of, and then I'll move some stuff around. Let me put r squared dm, and that whole thing is in parentheses. This is the integral that we have to do, times omega squared. So this quantity in brackets will actually be your operational definition of the moment of inertia. This will be your starting point for calculating moments of inertia. And truthfully, that's not the emphasis of your final exam. You may have one problem where you have to calculate a moment of inertia, but more often we are just quoting the result for some common shapes. So moment of inertia, and it doesn't matter if you write the r squared first or the dm. I'll put the dm first, even though normally in calculus you write the differential at the end here. I'm going to say take each mass, each little piece of mass, and multiply by the square of its distance from the rotational axis, and then integrate that. Now, I must emphasize that this is a symbolic expression. This is not ready to integrate. Oh, I thought that was possible. Okay. This is a symbolic expression. What does it even mean to integrate r squared with respect to m? Would you have any idea how to do that if that showed up on your first semester calculus exam? You know, it's meaningless. We need to be integrating some expression with respect to the same variable. So it's going to be up to us in a variety of problems to turn this into something that can actually be integrated. And I'll show you a couple of examples here in this video. But first, let's start not with the integral, but with the discrete expression. And for that, I'll use this silly little thing I made for 3C. We were talking about diatomic molecules like nitrogen in air. So these are two Christmas ornaments. Believe it or not, I still have a tree up. What is this, May 15th? At this point, I think it would be easier just to leave it there all the way until December of this year, then I don't have to buy another one. Have you ever done that? Okay. Let's suppose that this thing is being rotated about this axis. See this axis coming out of the page here? That's the axis about which this thing is being rotated. So if we look at it from the side now, here's the axis of rotation. What I have to do is take each mass and multiply by the square of its distance. I need something to point with. The square of its distance from the axis. So now this itself is an extended object, but let's just treat it as a point particle. Treat this ornament as just a dot at its center. So we have to figure out how far the center is from the axis. That would be our r. We take this r, square it, multiply by the mass. Do the same thing for this one, and then add it up. So let me draw a picture. And I can estimate these distances here. It looks like the distance between the axis and the center of each ball is something like, I'll call it 3 centimeters. So axis, and I'll try to be fancy and give the picture some perspective here. We've got one ball on the back side, and here's the other one. And they're both joined by some, we'll call this a massless rod. I'll call this M1, mass 2. Oops. And then this is R1. It's the distance of mass 1 from the axis, and this is, of course, R2. How massive are these? In this case, they're equal. I'll just call them each M, and I'm guessing it's like 2 grams each, so that would be 2/1000ths of a kilogram. And I already established that the radii for each are the same. I'll call it R, and those distances would be 3 centimeters, so 3/100ths of a meter. Let's calculate the moment of inertia for this pair of Christmas ornaments about this axis. Notice I'm saying about this axis because the moment of inertia depends on the axis. It's not like an object has just one fixed moment of inertia. The moment of inertia depends on the axis of rotation. If I made this same thing rotate about this axis, it would actually have a much smaller moment of inertia because the mass is all clustered more closely to the axis. Here, the mass is distributed farther from the axis. So the axis matters a lot. Okay? Moment of inertia is the sum over I of take each mass, multiply by the square of its distance, and that's going to be M1 R1 squared plus M2 R2 squared. And since it's the same for each, the masses are the same, and the R's are the same. Just for this particular problem, this just becomes 2mr squared. Okay, so that's 2 times 2 grams, but I'm using SI units, and then 0.03 meters squared. Can we do this in our heads? Not quite. This is 0.004, but 3 squared is 9 with 4 zeros. I think it would be best to use the calculator. 3/100ths squared times 0.004. And there it is, 3.6 times 10 to the negative 6. So 3.6 millionths of this unit, kilogram meters squared. That is the unit of moment of inertia, the kilogram meters squared. And there is no name for that. We don't have a cute name. Just like for momentum, the units are Newton seconds or kilogram meters per second. There's no special name just for those units. And one thing you should notice here is that for small object or even just everyday sized objects, you tend to be talking about fairly small numbers in SI units. You could choose another system of units where your numbers come out bigger, but in SI, the moment of inertia of things like pizzas, I'm always going to pizzas, and this silly example, and even automobile tires, for instance, as they rotate, you tend to be talking about smaller numbers. It's not until you're looking at, I don't know, large wheels on a truck or an industrial flywheel or certainly planet Earth that you get really big numbers for moment of inertia. And this is something that we would measure in a lab if we had lab, but thanks to that stupid virus, it's all going to be on paper. Okay, that's an easy example for discrete particles. I think it's time now to look at a situation where we have to use the continuous definition of moment of inertia. First up is the old thin rod. This is probably the easiest one. So I mentioned a moment ago, I was talking about the ruler, right? You can rotate the ruler about this axis or an axis through the end. Let's go with an axis through the center. So imagine this thing revolving around that axis. And because it's revolving, each little piece of the ruler, except for the piece at the center, each little piece is moving through space with some speed. That means each little piece has kinetic energy. We are interested in the total kinetic energy. Now, half the work has already been done for us. We've already written this general expression, K rotes ma goats is 1/2 I omega squared. Let me give it a little angular speed omega there. It's the I that we need to determine. How is this mass distributed for a ruler rotating about an axis through its midpoint? Here's how we proceed. First of all, let's label the length of the whole thing here as L. Capital L will be the length of the whole rod. And I'm going to go ahead and set up a coordinate system here. This is the positive x-axis off to the right. And I'll put the origin right here. Let's take a representative piece of mass. Remember, it's infinitesimal. Since we don't have like 20 or 30 point particles here, the mass is distributed uniformly, or I should say continuously, throughout the rod. We have to use calculus. We got to use that differential notation. So I'm going to call this D capital M. Capital M will be the total mass of the rod. And it really doesn't matter if you use capital M or lowercase m. But since I'm going with capital M, D capital M will be the mass of just this infinitesimal piece. Now, here comes the most difficult part here, unless you get some practice with it, and then it's really not bad. I'm actually getting ahead of myself. Let's first just start with the definition. Moment of inertia. We take each piece of mass, dm, and multiply by the square of its distance from the axis of rotation. That was the symbolic expression that I wrote down just a moment ago. We have to turn this into something that we can integrate. Well, the first thing we can do is recognize that since I'm using the letter x for this axis, the distance of this little piece from the axis of rotation would just be the absolute value of its x-coordinate. The distance of each piece is just its x-coordinate, and we need the absolute value because for a little piece over here, for instance, its x-coordinate would be negative, but distance is positive. So that means we can rewrite this as absolute value of x squared. Now, this still is not something that we can integrate. What is the integral of x with respect to m? That's nonsensical. But if we could turn this dm into something that had a dx in it, then it would start to look familiar. X squared dx, that's something you can integrate. So here is the part that might be most difficult for some of you. And usually it involves setting up a ratio. So can we agree that a good label for the thickness of this infinitesimal piece would be dx? After all, if this is the x-axis, when you're on the left side of this piece, you're at some coordinate x, and then you scoot a little bit to the right side of this piece. That would be x plus dx. So the thickness here is dx. And if you could just remember the following logic here, you should always be able to turn your dm into something integrable. I'm going to suggest that the length of this little piece, or the thickness of this piece, compared to the length of the whole rod, should be the same as the mass of that little piece compared to the mass of the whole rod. It's simple proportional reasoning. And of course, it only works if the mass distribution is uniform. Like if this piece of the rod was made out of lead and this part was made out of lightweight wood, then this reasoning isn't going to work. It's got to be the same material throughout. Okay, what we've accomplished here is we found a ratio or an equality that's going to allow us to rewrite dm in terms of dx. So if I move some stuff around, I find that dm is m over L times dx. And this quantity here is called the, oh, gotta sneeze. Okay, quantity is called the linear mass density. It's the total number of kilograms per meter. It tells you how dense this thing is, right? If you've got 10 grams for every millimeter, for instance, that's a fairly dense rod. It's the mass density. So you just take how many kilograms there are per meter and then multiply by the thickness of this little piece, and that'll tell you how much mass there is in that little piece. So now we could say the moment of inertia is the sum of, we take our dm, which is m over L dx, times the absolute value of x squared. And this is really starting to look like something that can be integrated. So what's the next step? Well, these are constants. We can pull those out. And we really need to turn this into a definite integral. If we're going to account for the whole rod and only the rod, we need to choose limits. So think about that carefully. Look at the picture. We're adding up each little piece of mass times the square of its distance from the axis. And we're doing that all the way out to here and all the way out to here. So since this is the x-axis, I hope you can see that our limits will be from negative L over 2. Remember, the whole thing is L. So negative L over 2 to positive L over 2. So I've pulled out the m over L, integral of absolute value of x squared dx from negative L over 2 to L over 2. And at this point, many of you would know how to proceed because you've had lots of practice in calculus. But what's the general shape of absolute value of x squared look like? If we were to graph that versus x, isn't that just a parabola? Because when x is a negative number, it's positive. That's true even if you don't have the absolute value. So what we're really finding is the area under this curve from negative L over 2 to L over 2. And because that curve is symmetric with respect to the vertical axis here, and don't be confused, we've got axis of rotation in this picture. That's a physical axis of rotation. And then I have two axes in my graph of x squared versus x. Those are two different types of axes. Well, since this function is symmetric, that's called an even function, by the way, because even powers of x are even functions. They're symmetric. All we have to do is one side of the integral and then double it. Let's just take the area on this side and double it, and that will be the same as this. So the moment of inertia would be 2 times. I'd have to double the integral from 0 to L over 2. And I can throw away the absolute value signs now because x squared is the same as the absolute value of x squared. I could have done that previously, as a matter of fact. And we're practically done because you all know that the antiderivative is x to the third over 3. So that's 2/3 m over L x cubed from 0 to L over 2. Plug in your limits. Well, we're going to have an L cubed over 2 cubed, which is 8. 2 over 8 is 1/4. 1/4 times the 1/3 is 1/12. 1/12 m, and you see how L cubed over L is L squared. There it is. I of rod about center. So that's my shorthand way of saying the moment of inertia for a rod being rotated about an axis through the center is only 1/12 ml squared. Is it worth memorizing? You'll see it again. It's more important to know how to get the result. Well, they're both important, really. So maybe what you can do now is take a moment and repeat this calculation for an axis through a different point. Instead of rotating the rod about the middle, you should try rotating it about one end. This is too long. So instead of this, rotating this way, what if you were to rotate something about an axis through an end point? And you have some physical intuition here. You know that it's a little more difficult to do this rotation than it is to do this rotation. It's trivial for a pen, but imagine like a pool stick. It would be harder to rotate, whip it around an axis through one end. So I'm not going to go through that. You should pause the video. And I'm sure this is presented in your book. This time, let the axis of rotation be here. Choose your representative piece of mass with thickness dx. And repeat the calculation. And you know that it should come out to be a different number because physically, it has more rotational inertia in that configuration. In fact, you might even ask yourself, where'd that formula go? I go back to the result here. We should still have an ml squared in there because the mass and the length don't change. It's got to be this number that changes. So what's that new number going to be? Now, while we're on the topic, let's apply this notion of rotational inertia to the familiar example of a tightrope walker. If you were this dude standing on this this rope here, that would never be me personally, but if your arms were down, we've all walked on narrow walls as kids, I'm sure, or the boundary between, 1 yard and the next. You know what I'm talking about. You've walked along some kind of narrow path and sensed that if your arms were down, it's more difficult to maintain your balance, or this person would have a greater tendency to fall off of the tightrope. So if you think about it, if this person were to tilt to their right and start to fall, wouldn't their body begin to rotate about this axis, an axis coinciding with the rope? Hopefully you can see that. It would be easier to demonstrate in a classroom, but this person, their whole body is going to start to rotate around this axis. And in order to give themselves time to react, that fall needs to be as slow as possible. In other words, in order to maintain your balance, to give yourself as much time as possible to react, you need a larger rotational inertia. So it's instinctual for animals, including ourselves, but when you throw your arms outwards, what you've actually done is put more of your mass farther from the rotational axis. When his arms are down, the mass of his arm is closer to this axis. So when you look at the prescription for calculating moment of inertia, you take each piece of mass, multiply by the square of the distance. All the R's, or at least the R's for the particles in his arm, those R's would go down, and that means the total rotational inertia of his body about this axis would be smaller. So that's really what's happening. By changing the shape of your body or the orientation of your body, you're changing your moment of inertia. And in this situation, you would want to increase your rotational inertia because we're going to see that the greater the rotational inertia, the longer it takes to speed up rotationally. And that gives your body time to react. Now, there's a limit to how large your rotational inertia can be, right? You can only throw your arms out so far. So that's where the rod comes in, or the pole, tightrope walker's pole, rod, whatever you call it. Look how far the mass is on the end of this pole from the rotational axis. Again, I'm imagining the rope to be the rotational axis because if this woman started to tip over, she would be rotating about an axis coinciding with the rope. So by holding that pole in that configuration or orientation, she's drastically increased her rotational inertia about the axis. Let's look now at arguably the most useful and most common shape for which we'd like to know the moment of inertia. This would be a solid disc with an axis through the center. And I think it's fairly obvious why that's so useful. Wheels, that's the most common application. I guess you could go back to the pizza here, or even the Milky Way galaxy. We would like to know the moment of inertia for a solid disk rotating about an axis through the center. So I'll draw a little representative piece of mass. I'll call this dm, and I'll draw its particular radius. Remember, it's tracing out its own circular path. You can see that the radius of the circular path is equal to how far that piece of mass is from the axis. And the whole idea here is to take each little chunk of mass within this disk and multiply by the square of its distance from the axis, and then add all those up. That's how you calculate moment of inertia for the disk. And we're going to see a very simple formula plops out. It's a lot like the 1/12 ml squared in the case of a rod rotating about an axis through its midpoint. Okay, well, let's take a top view here. Let's look down on the disk. Here's the axis coming out of the page here. Here's a particular piece of mass with radius r, and I'm not going to label it yet. So we go back to this definition. Remember, you can't integrate this unless you cast it in a different form. What is the integral of r squared with respect to m? That's meaningless. We need to turn the dm into something that has, ideally, a dr in it. If it was r squared dr, that's something we could integrate. Okay. What's the best way to go about explaining this? I'll just show you where I'm headed. I'm going to make this a little bigger. So imagine a hoop. This is a terrible drawing. Imagine a hoop here, which you can break up into, I don't know, 100 pieces and call those pieces M1, M2, M3, M4, etc., all the way around. And at least for that part, remember, you'd have to do this for every little piece throughout the disk, but at least when you're applying that to these, you'd have M1 r squared plus M2 r squared plus M3 r squared, where I'm imagining this is M2, this is M3. But notice how I didn't have to put subscripts on the r's because each of these little pieces shares the same radius from the axis of rotation. And that means we could factor out the the r squared. And then at the end, multiply by r squared. So just add up all the masses in this hoop, and at the end, multiply by r squared. So it's like, in a sense, you've already done the sum over the hoop. And perhaps that's not the best way of presenting it, so here's another way to think about it. Your dm doesn't have to be this little rectangular chunk. In this case, the dm can be a hoop of infinitesimal thickness. Since every piece of this hoop shares the same distance from the origin, we can think of it as one little piece of mass. And since it's infinitesimally thin, I'm still going to call it dm. So dm is the mass of this thin hoop. Now, how much mass is that? It's infinitesimal because it's infinitesimally thin. It's that strange calculus notion. And it's got a particular radius r. Now, you could see that if I had made the hoop larger in diameter, r would change. Presumably, dm would change as well. So r depends on which particular hoop you're talking about. Okay, now we need to figure out how to express dm in terms of r if we have any hope of integrating. So remember the trick before? I wrote down a simple statement of proportional reasoning. Let's do the following. dm compared to m, where m is the mass of the entire disk, total mass of the disk. If we compare the mass of this ring or hoop to the mass of the entire thing, dm compared to m, that should be the same as some other ratio. Well, what would that ratio be? Previously, I said for the rod, it was dx compared to L. Let me see if I can find that. Let's just rewrite it. I said dx compared to L was dm compared to the entire mass. Can we make a similar statement here? Well, a rod is one-dimensional. Now we're talking about a two-dimensional problem. So perhaps it would be the area, dA, of this thin hoop, excuse me, compared to the total area of the disk. It's still that same statement of proportionality. That's our starting point for turning this symbolic integral into something that we can actually integrate. Okay, now how do we proceed? The thickness here, what would be a good label for the thickness? Since it's infinitesimal, and as we move outwards towards the edge of our disk, r is increasing, perhaps dr would be a good name for the infinitesimal thickness of this hoop. And now what I'd like you to imagine is taking some scissors, cutting that hoop, and then unrolling it and laying it flat right here. Oh, that's not good. This looks like the rod that I drew earlier. Horrible picture. That's this hoop after it's been cut and then rolled out flat. Well, the thickness here, we already agreed was dr. So dr is like the height of this skinny rectangle. And what would the length be after you've rolled it out? This length is equal to what we call the circumference. And you all know that to get circumference, you take radius and multiply by 2 pi. 2 pi r is the circumference. So that hoop is a lot like this skinny rectangle. And that means that we can say that the area of the skinny rectangle, which originally was this thin hoop, would be base times height, or 2 pi r dr. Circumference times dr. That is the area dA of this infinitesimal piece of the disk. Okay, so let me rewrite this expression. dm compared to m will be dA, which we just established as 2 pi r dr, compared to A. Well, what is capital A, the total area of the disk? You all remember pi r squared. So let's use capital R now for the actual radius of the disk, the outer radius. Down here, the total area would be pi big R squared. And now we've got an expression for dm. We've turned our dm, or we've expressed dm in terms of dr. So when we put it in here, we will be prepared to integrate. So dm is equal to, let's see, the pi's cancel over here. I've got a 2m over big R squared times little r d little r. That's just this rearranged. Let me substitute that now into here. Now, this is not obvious, right? I certainly don't look at this problem and immediately recognize what dm is. I had to write down this statement in order to get there. Okay, the moment of inertia will be, let's pull out the constants. I would plop all of this in for dm, but I can pull out the constants. The mass of the disk is a constant, so is the outer radius of the disk. And lastly here, I still have the r squared, but don't forget about r dr. R dr, r squared. This came from dm, right? This was part of dm. Well, we can simplify this. That's an r cubed dr. We're practically done. The last thing to do would be to choose limits of integration. So we go back to our picture. Maybe I could draw a new picture right here. What we've actually done is we've found the moment of inertia of this little hoop. We imagined a hoop of infinitesimal thickness dr, find its moment of inertia, then go out to the next hoop of slightly greater radius, find its moment of inertia, and so on until we get to the edge. So you're really taking the moment of inertia of each hoop and stacking up all those hoops, summing up their moments of inertia. I could have even just said this. Total moment of inertia is the moment of inertia of di, where di is the moment of inertia of each hoop. That's another way to think about it. Okay, what are the limits of integration? Well, little r is a variable. We can go from the innermost hoop, which has a radius of practically 0, all the way to the outermost hoop with the radius big R. So from 0 to big R, and you see where this is going. The antiderivative is 1/4 r to the 4th. And I'm going to skip the step where I put the brackets and the limits. You can see that when you plug in 0, that goes away. So it's really big R to the 4th over 4. 2m over big R squared times big R to the 4th over 4. 2 over 4 is 1/2. Pardon me. And we've got 1/2 mr squared, which I really think you should memorize because it shows up so much. 1/2 mr squared, where m is the mass of the disk, and r is the radius. That is the rotational inertia specifically for an axis through the center. That's important because a circular disk could have a different moment of inertia if you forced it to rotate about this axis, for instance. That would be kind of awkward to have this thing spinning around that axis, but in that case, the moment of inertia would be a different quantity. So this is a disk about an axis through the center. And this quantity tells you something about how difficult it is to get that thing to rotate. The greater the rotational inertia, the more difficult it is to get it rotating about that axis. Or we'll see the more torque is required. That's a concept we have to define later in the chapter. Okay, I'd like to immediately use this to solve a problem, but let me contrast that real quick. Contrast that with an actual thin hoop. What if instead of a solid disk where the mass is distributed throughout the disk, what if all the mass was at the edge? Can I even draw that? Let's see here. Yeah, so let's suppose that this is made out of something heavier, like the solid disk was made out of wood, and this hoop is made out of metal. So even though it's smaller in volume, it's just the outer edge instead of the whole thing, it still weighs the same. So it's still got mass m. But let's pretend it's so thin that, you can see an actual thickness here because I had to draw something. Pretend that the thickness is almost 0. Then when you go to do this, dm r squared. Oops, that's supposed to be a lowercase r. Take each little piece of mass throughout this thing, multiply by r squared. Doesn't every piece share the same distance from the axis? Since all the mass is at the perimeter or the edge, every piece of mass has the same value of r, it's big R. So this is actually a constant for this particular calculation. And that means we can pull out the constant. This line of reasoning is only applicable to the thin hoop. What does it mean to integrate dm? Well, that's symbolic for add up all the little pieces of mass. What do you get if you add up all the pieces of mass? That would just be the total mass. So that's mr squared. So the moment of inertia of a thin hoop about an axis through the center is mr squared instead of 1/2 mr squared. Why the difference? Again, it's all about the way the mass is distributed. Look at the formula here. The more of your mass you have farther from the axis, the greater the moment of inertia. For the solid disk, a lot of the mass was not actually out at radius big R. Some of the mass was right here, going around in a circle like this. Some of the mass was right here. So that 1/2 captures the distribution of all the mass. It's not all actually out at radius big R. Some of it's at a much smaller or a considerably smaller distance. Okay, those are two moments of inertia that should be fairly easy to memorize. In fact, in general, because you could have a circularly symmetric mass distribution that's something in between a hoop and a solid disk. What about a bicycle wheel with a hub and spokes, for instance? That is the worst drawing. I think I can do a little better than that. Okay, hub, wheel. I don't know, looks more like a wagon wheel now. Some of the mass is at the center, some is at the edge, some of it is distributed in between. I would expect this moment of inertia to be not necessarily 1 times mr squared and not necessarily 1/2, but something in the middle perhaps. So I'm just going to call it some unspecified constant c mr squared, where 0 is less than c is less than 1. C would have to be some number between 0 and 1. So this is going to show up often. A circularly symmetric object where big R is the outer radius of the object, your overall moment of inertia is going to be some constant times mr squared. And that allows you to do some general calculations, which is what we should do next. Before I present an actual problem using that formula, there's an important relationship we have to look at. The formula that we get here is going to look familiar to you, but it's for a different a different result, even though it looks identical to something we've already seen. Okay, so here's a solid wheel rolling without slipping. Rolling without slipping. So rolling motion is just a continuous replacing the point of contact. Right now, it's this point on the wheel that touches the ground. A moment later, this point on the wheel is going to be the one in contact with the ground. So in 2 dimensions, a perfectly rigid wheel only has one point of contact. Of course, for an actual wooden wheel, even if it was perfectly rigid, there'd be a line of points of contact going into the page. So let's just suppose that the center of mass, the center of this wheel, moves from here to here in a time dt. And I'm going to call this distance delta x. And the expression for the center of mass of the wheel, v, we haven't defined center of mass yet, but I think you all know that for a circle, the center of mass is at the center. Well, that would just be the distance traveled over this time interval, which I'm calling delta t. And we can relate that, we'll see, to the rotational speed omega. So the observation that you should make, here's radius big R, big R. Try to imagine that as this wheel rolls forward, it's moving, the whole thing's moving to the right. This is the velocity of the center of mass. I tried to draw it so that you can see this. All of this arc length is going to be rolled across here. So the distance that the wheel moves in time dt, delta t, is the arc length from here all the way to here. See how this radius, if you had painted a line on the wheel, that line would have rolled around clockwise until it ended up pointing vertically downwards. So let me call this arc length S. That's the arc length all the way from here to there. I'll correspondingly call this angle theta. And again, we know from the definition of an angle in radians, theta is the arc length compared to the radius, which means that the arc length is r times theta. Hopefully that's something you already know. But arc length is delta x. Remember, in order to move from here to here by rolling, this arc length has to be rolled out flat over the surface. So s and delta x are the same thing. So now we can say that the center of mass velocity, instead of delta x, I can write s. That would be s over delta t. And now, what's next? Here's where we make the substitution. Right, okay. Maybe I should call this delta theta. You'll see why in a second. Delta theta will be the angle through which this painted line turns through as the wheel rolls through this distance. Okay, so now I can substitute, instead of s, I can write r theta, or now I'm calling it r delta theta. And maybe you see now why I chose to go with delta, because now it's easier to recognize change in angle over change in time. We're talking about radians per second, revolutions per minute. Oh, I shouldn't say that because we have to use SI units in order for this to be valid. This is omega. So we recover a formula that looks very familiar. R omega. Doesn't that look like the formula for tangential speed for a part or a particle in a rigidly rotating object? This is a different scenario though. This is not we're not talking about the speed of an individual particle within a rigid object in terms of the angular velocity. We're actually talking about the velocity of the center of mass of a rolling wheel in the case of rolling without slipping. So it's the same formula, which will help you memorize it, but it's really a different formula. Again, this is only true for no slipping. Because what if, isn't it possible, what if this was an icy surface and your wheel, couldn't you like kick the wheel at the middle and get it to skid without rolling? You know, it could be skidding without turning at all. And if it's not turning at all, omega would be 0. But the velocity of the center of mass would not be 0. That doesn't work, right? How can you have some number that's not 0 equal to 0? It doesn't work. That's because this equation would not be valid in that case. This is only applicable for rolling without slipping or slippage, whatever you want to call it. Okay, now we're prepared to solve an interesting problem with these results. Consider a ramp with inclination beta. I don't want to use theta because I was using theta for angle turn through by a disk. And here's a disk at the top. And let's say that the height of the ramp is h. The disk has radius big R, and it starts from rest, and we allow it to roll without slipping. And then we'd like to know what's the velocity at the bottom, v final, I'll call it. And that would have to be in this direction. It's, you know, it's rolling parallel to the ramp. What is the velocity at the bottom? Okay, now if this was a chapter 11 problem, you would probably immediately think in terms of energy conservation. You'd ask, are there dissipative forces? If there's no mention of air drag, we can throw that out. And if there's no kinetic friction, we would not have to worry about energy dissipated by kinetic friction. And then we could say, let's see, I think it was work external is delta E thermal plus delta E mechanical. We'd say, no dissipative forces means that is 0. And then there's nobody pushing on this disk. There's no ropes pulling on it. There's nothing that falls under the category of a so-called external force, so that's 0. And that means we're talking about an energy conservation equation. We would say that the total mechanical energy at the beginning must still be there at the end. And we would recognize that if we put the origin down here, a y coordinate of 0 at the bottom of the ramp, we would recognize that this disk starts out with gravitational potential energy. And at the end, all of that energy has been transformed into kinetic energy. And we could use that statement. So we would say, if the mass of the disk is m, we could say something like mgh is equal to 1/2 m v final squared. V final would be root 2gh. But that would be incorrect. This is the naive answer, because when we did this for the early part of the semester, we totally neglected the energy that's associated with the rotation. All we talked about was the so-called translational kinetic energy. If you look at the disk as a whole, yes, it's moving sideways, and so it's got kinetic energy due to its translation. Just to be clear on that, right now I'm translating the pen. This is rotation, and then this would be a combination of the two. I think across the screen and rotating would be translation and rotation. Now we have to account for rotation as well. So think about it. Before this thing starts to roll, yes, it's got this much potential energy. And there's a very subtle point here. I don't want to throw too much at you at once, but this mass, it doesn't really have one particular y coordinate, does it? Isn't the center of the disk at a lower y coordinate than the top of the disk? And this is at a lower coordinate still. So which y coordinate are we supposed to use? Well, it's actually the y coordinate of the center of mass. So I probably should have drawn this so that this dot here was level with the top of the ramp. If you're going to use mgy for the potential energy, the y coordinate that you use should be the y coordinate of the center of mass. I'll try to show that later in another video, but it is shown in your book. Okay, some of this energy is transformed into rotational energy. This thing is rotating at the bottom because it's rolling. And that means not as much is available for translational energy. So there's no way that the translational energy will be as great as this at the bottom. Some of that energy has to be taken up as rotational kinetic energy. So we need to go back to our statement of mechanical energy and try again. So I will say that the change in mechanical energy is 0. And that means potential energy initial plus kinetic energy initial has got to be potential final plus kinetic final. Even though the kinetic energy may be changing and the potential energy may be changing, the sum should not change. That is the statement of conservation of mechanical energy. Okay, because of my choice of origin or coordinate system, at the end is when the potential energy has a value of 0. I could have put y equals 0 up here, in which case the potential energy up here would be 0, and the potential energy down here would be a negative number. So our equation would look different at first, but when you solve for the answer, you would still get the same answer. It all works out the same. So the answer is not dependent on your coordinate system. Okay, I'm going to cross out the final kinetic energy, or potential energy, for that reason. And the The initial kinetic energy is 0 because we're assuming that this thing starts from rest before it starts to roll. And here's where we plug in mgh for the energy that we start with. And now at the end, we've got to break this up into two parts. There's K translational final, the final value of the translational energy, and the final value of the rotational energy. This is the term that changes the result. We're not going to have the simple root 2gh that we expected. Okay, well, I haven't talked about this yet, and I'm not going to prove it here. Your book, I believe your book also does not prove it. They just quote the result because it's fairly intuitive. When you look at the total kinetic energy, remember, as this thing is rolling, if you look at one individual particle, isn't it doing something kind of fancy? It's doing these loop-de-loop patterns. Actually, there's a specific shape that has a name. It's called a cycloid, which is pretty cool. I think that's actually a point on the rim. Yeah, it's the point on the rim that traces out the cycloid. So this scribble I drew is not really a cycloid. The cycloid looks like this. It's got an interesting history in mathematics, or math and physics. And where was I? Each of these particles has got some fancy shape that it's, or trajectory that it's tracing out. And the idea is at any moment in time, this piece has a particular kinetic energy, this other piece has a particular kinetic energy, and you'd have to add up all those kinetic energies. Sounds really complicated, but it's in practice, it's simple because you can divide it into two types. All you have to do is look at the 1/2 I omega squared energy from rotation and the simple 1/2 mv squared energy associated with translation. That's it. So for translation, it's still just 1/2 mv squared, but the caveat here is the m is the total mass, and which speed are you supposed to be using? Because the speed of this guy is going to be different from the speed of this guy at any given time. Which velocity are we supposed to use? You guessed it, the velocity of the center of mass. It's almost, you know, it's like the first thing you would guess, so I often forget to point this out in class, but the translational kinetic energy, you take the velocity of the center of mass, square that, multiply by the total mass. Okay, let me plug that in. K translational would be 1/2 m, the velocity of the center of mass at the bottom. And this is getting a little cumbersome with the notation. And now we use the formula that we now have for rotational kinetic energy. That's 1/2 I omega squared, but specifically that's omega final squared. Okay. The whole point here was to find the final speed. I want to see if it actually is root 2gh or something else. I think it's obvious already it's something else. How do we proceed here? Because it looks like, you know, suppose we were given the mass and the radius of the disk, and even that coefficient c. Your book doesn't use this. I should emphasize that. This is my little letter. I remember for a disk, because I didn't actually specify if this was a solid disk or a hoop or like the bicycle wheel with spokes. Let's just assume that it's some number times mr squared. That's how you would calculate the moment of inertia of this circular object. Some number between 0 and 1 times mr squared. Okay, so supposing we're given all three of those quantities and, of course, the height of the ramp, because the higher it is, the faster you would expect it to be going. Can you find the speed at the bottom? Well, let's ask ourselves how many unknowns appear in this equation. We do know the mass, presumably. We know 9.8. We know the height that was given. We don't know how fast the center of mass is going at the end. So I should really specify V center of mass final. We also don't know the angular velocity at the end. And we don't know the moment of inertia. They didn't give that to us directly. So that seems to be 3 unknown quantities. But remember, we can relate the translational speed to the rotational speed if it rolls without slipping. Only if that's true. If this thing is skidding on the way down, like it's barely rolling, but it's moving real fast, then that's no good. You can't use the formula. But because it's rolling without slipping, we can say that the velocity of the center of mass equals r omega. Also, we have an expression for the moment of inertia of this circular object. It's some number times mr squared. Let me make those substitutions. instead of V center of mass squared, that's R squared omega squared. And I is some number C times big R, nope, big M, big R squared. And then, and I really should have labeled this R, excuse me, omega final squared. This is the final omega, and we don't know what that is yet. It looks to me like the M's cancel out, and the only unknown left, if we're given this coefficient C, would be omega. So let's solve for omega, and at the end we can just convert that back into V center of mass. I find that the M's cancel. Let's factor out omega final squared, or we can just think of it this way. Yeah, we do need to factor. So GH is equal to omega final squared times, actually what I can factor out is a 1/2. See how both terms have a 1/2? So I'll put 1/2 omega final squared times, darn it, I could have factored out the R squared as well. You're probably better than me at this. 1/2 R squared omega final squared times 1 plus C. All right? So omega final squared, if I move some stuff around, I have a 2GH over R squared times 1 plus C, semicolon. I always feel sophisticated when I use a semicolon. Whoa, you can see the sun's coming down. Look at all these patterns of light coming through the blinds there. You know what's really cool? You can't see it here, but because I'm looking at my blinds right now and the gaps between the blinds are rather large. But if I close my blinds a little bit, or the sun was in a different position, if the gaps between the blinds were small enough, all of these square patterns would turn into circular patterns, because what you'd actually be looking at is an image of the sun, which is really cool. Totally off topic, but you could take a shoebox, put some tissue paper in the front, no, tissue paper in the back. This would have to be something opaque, like regular cardboard. Poke a little hole in it, and even if that hole is square shaped, as long as it's really small, you could point this at something bright and see an image on the back where the tissue paper is. So square hole, point this at the sun, you would actually see a round image of the sun. And that's what I'm talking about right here. If the gaps in my blinds got any narrower, these squares would turn into circles, which is kind of fun. Okay. Here's where I use this result. V center of mass is radius times omega. That's for rolling without slipping. Well, if I square both sides, R squared omega squared, now I can recognize, if I put this R squared over here, wouldn't I have R squared omega squared, which is V squared? Okay, I think I've determined that the center of mass squared, speed of the center of mass squared, is 2GH over 1 plus C. And so the speed of the center of mass at the bottom has been reduced by a factor of root 1 plus C. So the speed is in fact less than we would get from the naive analysis earlier in the semester, where we treated everything as a point particle. This is no longer a point particle, it's an extended object, which has, by virtue of being an extended object in space, it's got its own rotational energy, not merely translational energy. So the bigger C is, the greater the denominator is, the lower the speed at the bottom. What's all that about? Well, remember C, this, I like to call it C, this coefficient tells us how the mass is distributed. And just to remind you, for a solid disk, the moment of inertia was 1/2 mr squared. In other words, the coefficient of C out front was 1/2. And for a hoop, worst drawer ever, only because I'm not trying. My focus is elsewhere, right? Thin hoop, the moment of inertia is the full mr squared. That means the coefficient C is 1. So basically, the more of your mass is at the edge rather than towards the center, the higher the value of C is. And according to this result that we just calculated, the higher C is, the lower the speed is at the bottom. So a hoop would be going slower at the bottom of the ramp than would the solid disc. And that's not really intuitive. We don't have a lot of experience with that in everyday life. Why is that? It's because when it gets to the bottom, where's the original picture here? Something that has a higher rotational inertia, when it gets to the bottom, more of its initial gravity energy is tied up in rotation than translation. The greater the rotational inertia, the more of your energy winds up as rotational kinetic energy. Now, later in the chapter, we can come back and reanalyze this using torque and angular acceleration. That's another way to think about it. That's the dynamical perspective. Right now, we're thinking in terms of energy conservation. So let me pull up a video of this phenomenon. Okay, I'm going to let this guy do the talking.
Well, that's happening. Let's take a look at this demonstration right here. Here I've got two discs which have the same radii. One of them is an aluminum ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disc. What we're going to have them do is race down this incline, and the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is 0. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is.
Okay, let's think back to what we just did on paper. The formula was root 2gh over root 1 plus c. So the higher the value of c, the lower the speed of the center of mass at the bottom. And remember, the hoop here has a higher value of c. C would be close to 1 for the hoop. So we would expect this one to have a smaller speed or a lower speed at the end. Now, maybe this is an obvious point to you, but the one that's going fastest at the end, wouldn't that be the one that got there first? Because if the wooden block is going faster at the end, then presumably it was going faster the entire time. And that means it would have gotten to the end first. Okay?
So the wooden disc rotated more quickly and won the race down the incline. That makes sense because we said that the metal ring had greater rotational inertia, so there's a greater resistance to a change in its state of motion. It's going to have a smaller rotational acceleration as it goes down the plane. Let's take a look now.
Bye-bye.